today we're going to talk about waves, but before I get to that, I want to do a little bit, namely a situation where you had a box that you pushed down on water. And because there's still a little bit of confusion on notation there, and I'm not sure everybody really got that. So I want to make it very clear. All right? So I'm going to draw 3 pictures. The first picture is the box sitting there at equilibrium. We'll call this y equals 0, and this distance would be y equilibrium. Okay, so that's the first picture. The second picture is this picture. We press down on this at distance d. Okay, so now this point here is y equilibrium minus d. All right, and if it was pressed down, right? So y equals 0 is over there. And this little distance there is d. All right, so I pressed it down below so that now the point that was originally here, this point here, is now down here at minus d. All right, is that right? Everybody agree with that? I want you to disagree. What is wrong with the picture? All right, so first of all, we don't want to change our origin, right? The origin is where the water, surface of the water is. Here, I changed that. That's not good. Right, so that's a bad picture. All right, so let's fix this picture. This point is still y equals 0. This point, though, is y equilibrium minus d, because you pushed it down. The point is that if I put a dot on here, right, a dot on the object, that dot has moved down. All right? And this distance here is d. I'm keeping my same origin. The top has moved down because I pushed down on the object. I pushed down, so the top moves down. So y is not at y equilibrium. It's at a lower distance. Now we need a third picture, because this d is not a variable. This is where the confusion comes in. This d is not a variable. All right, so I'm going to draw a third picture. That's y equals 0. Now, once I press this down and let go, what is going to happen to the object? Is it going to go down or up? It's going to go up. All right, so I draw another picture where it's somewhat higher. So I'm going to try to put that there. So I'm a little higher up there. Okay? So this guy here has moved up a bit. All right? And I have a little distance here, which I'm going to call x. X is not the same as d. X is a variable. D is just the initial displacement. All right? So now I have this variable x. All right. Now remember, your goal is to get an equation that looks like this. That is the goal. So this is the goal. And we're going to use Newton's second law to get there. All right, so we have to use Newton's second law. So Newton's second law boils down to m dx squared dt squared equals the net force. There's a force up and a force down. All right? Now, the way I've defined this, d is, so is d an x positive or negative or both? Over here, d is this distance down there. It's just a positive quantity going down. Over here, x is the distance this way. So my coordinate system for x is this way. All right, so x is going that way. Okay, positive x is down. I mean, I could do the other way, but it seems natural to do it this way, because that way d is a positive number down. So x is positive down. All right, so you have two forces, mg, gravity, and the buoyant force. If down is positive, which of those two forces is positive? I'm going to ask for a vote. It's either gravity or the buoyant force. So gravity is the positive force. All right, so you have gravity is just mg. And the buoyant force is negative. Force is pointing up, but we've decided that the positive direction. What is the buoyant force in terms of all the things on the blackboard? So we know it's rho of the water, g, right, gravity, and then the volume of the water displaced. All right, so this is L, and the area here is L squared. So we know there's an L squared. And the question is, when it's at x, how much is displaced? That's the question. What's the answer? All right, so at equilibrium, it's L minus y equilibrium, right? So what is it if we displace it by this x? It's going to be L minus y equilibrium, but somehow that x has to appear. How's that going to appear? Plus x, all right? Now here's one way of thinking about that. At equilibrium, you have L minus y equilibrium. That's how much is displaced. When I push it down, is more displaced or less? More. So you just add that amount, more, plus x. OK, so we have that. Now I'm going to rewrite this in a certain way to make things clearer. Everybody agree with what I did? Is the math OK? It's pretty straightforward. I isolated out the variable. That's one good point. This thing looks like, so this and this looks like what our goal is, right? Yeah. But how do we get to the goal? That's the key. That's a good observation. And that should help you understand how we get to the goal. This equals this, right? Very good. So this minus this equals what? 0, right. So we can cancel out this, because this equals 0. Right? That's how we got the equilibrium condition. We did this minus this. That's the definition of the equilibrium condition. And so we end up with dx squared dt squared equals minus rho g L squared divided by m times x. So we got our goal. And that says, I called it omega 0 squared, is equal to rho g L squared over m. All right? And then you can calculate the period. All right? And then when you want y of t, because that's what it's asked for. It asks for where the top of the thing is. It's equal to y equilibrium minus x, right? Because x is down, y is up. And then that's just equal to y equilibrium minus d cosine of this omega 0 times t. Here's where the D comes in. It's the amplitude of the oscillation. All right? It's not a variable. X is the variable. T is a variable. D is not. It's just the initial pushing down, which turns out to equal the amplitude, because there's no velocity when you let go. The logic, the strategy, the step-by-step is what's important, not the answer. And drawing good pictures, correct pictures, is very important. And I showed you a bad picture, because I want you to be able to distinguish between good and bad pictures. Some pictures are bad because they're not even correct. There's some inconsistency. Some are bad because they don't show things very well. They may be too cluttered, or they may be confusing. And some are bad because some of you sometimes are not very good artists, right? You don't draw well, and you have to work on that. It's a skill. I've had to work on it too. One of the best ways of improving that skill is to draw bigger pictures so that you can see what you're doing. Okay, so what are we going to do today? We're going to talk about waves. The topic we talked about was oscillations. Oscillations are things that vary in time. They're just oscillating in time. You know, you have a mass going up and down. What we have now with waves is we're going to have things that vary in time and space. T and X, for example. I'm going to just do this. Watch this. See, I can move this up and down. All right? So you see something changes in space. This is the spatial direction. And time. All right? You saw it change with time. All right? I can do a pulse. Yeah, let's do a pulse. Set up a little pulse there. And I can change all kinds of things. I can change its amplitude. I can make its amplitude bigger. Goes up bigger. I can make it smaller. Smaller. So I can do that. I can change the pulse width. I can do that. All right. I can get rid of any damping. All right. If I get rid of damping, what happens is the amplitude does not change. All right. We're not going to do anything with damping. We're going to do everything without damping. So we have a pulse that moves across. We can have any kind of shape we want. We can also have nice oscillations like that. All right, it's going around and around. And I can change all kinds of things. I can change the frequency. I can make the frequency bigger. I can make it smaller. Okay. There's a thing called a tension I can do. That changes things. Okay? And we'll discuss why all these things change the way they do. All right? Okay, so this is our goal. Understand this kind of motion. All right? Waves are everywhere. Do you see any? Are there any waves in this room right now? My voice is a wave, that's right. You wouldn't hear me if there wasn't a wave coming from my mouth to your ears. You would not hear me. All right? You wouldn't see me either, because light is a wave. It's the light from the light fixtures, right, is hitting me, bouncing off me, and going into your eyes. That's how you see me. All right? So light is a wave. All right? All kinds of water waves. You know, like you go to the beach, you see waves going up and down. Those are waves. Here's a wave on a rope, and we see that. You might see, anytime you see any kind of string or rope attached anywhere, usually there's some oscillations on it. So waves are everywhere. Inside a solid, there are waves going on. There's sound waves, there are other waves as well. All right? In physics, we have waves of charge, so-called plasmons, plasma waves inside certain kinds of materials or inside what are called plasmas. We can have even spin waves. It's like imagine spins inside a material. And the direction of the spin changes with time and space. They're called spin waves. And perhaps the most famous recent example of a wave, the first time it was directly discovered was about, 5 years ago. Gravity waves. That the fabric of space and time was actually oscillating. All right? Not by much. Probably smaller than the size of your hair. I think it was like maybe even smaller than the size of an atom. But they were able to detect this using a huge, big detector. Actually, two of them, one in Louisiana and one in Washington State in the US. And this is going to become a new form of astronomy. Gravity wave astronomy is going to become very big. All right, so what's our goal? Our goal is to learn how to describe these waves mathematically. I don't know if you remember when I first started teaching here, I told you that a lot of physics is about translations. Translations between the phenomena, pictures of the phenomena, mathematics, and language itself, English or Chinese, for example. Okay? So we're going to figure out how to mathematically describe this. So I'm going to start with describing any wave whatsoever, any pulse, anything. You can always write down that a wave can be described by the following function or a sum of functions like it. Okay? So I'm going to write it down. Here's a wave function. Y represents the displacement in this direction. So we have y, but it's a function of x and t. So x is in this direction, and t is time. Notice one thing. This is like a rope. Let me stop it for a minute. You see this green dot? Here you have green. Green there, green there, green there. When I let it go, I want you to just watch this green dot. Don't watch anything else. Everybody ready? Watch that green. Then I'm going to ask you, what does that green dot do? Everybody watching it? Maybe this is too fast. Let's make it slower. Let's do a lower frequency and make it a little easier. All right, so watch this green dot. What is that green dot doing? It's going. Which way? Does its x position change? Only its y position. All right, so that green dot is going up and down, up and down, up and down. Okay? So there's every position on the wave has a function that's a function of time. And also we see that things depend on where you are. So it turns out that a wave can always be described as either this wave function that I'm writing down or a sum of these. All right? And v is the speed of the wave. All right? So I'm going to let v be the speed. So any function like this. Here's an example. Example for that would be y equals a, let's say, sine x minus vt. All right? something like that. And I'm going to multiply it by some constant, I'm going to call it k. So that's an example. See, it's a function. Wherever x appears, it has to appear as x minus vt. Here's another example. Sigma is some constant, a is a constant. This is a Gaussian pulse, little pulse, a Gaussian pulse. That's an example. All right? I can make up any function you want. As long as it's a function of x minus vt, it's a wave, and will behave like this. So like if I want to do a manual, I can do that. What I did was make a wave. So let's get a little insight into what this means. What does this function mean? All right? So in order to get some insight, consider x equals 0 and t equals 0. So we have a function f of 0, 0 equals some f0, whatever it is. At what value of x, let's say we want to see when will the function equal that again. So we want to see at a later time, where is that peak? All right, so let me see if I can do this. Maybe I'll do a pulse. So here's the pulse. Let's say I define x equals 0 there. And right now I'm at t equals 0. Where would this peak be at a later time? Is it going to be over here, or is it going to be over there? Over there, right? The peak is moving this way. So what about this function? So now we have a function, x and delta t. All right, so if I stick that in there, I get f of x minus v delta t. Okay, everybody see that? I just put in. I don't know what x is. I'm trying to find out what is x such that this f equals this f0. So f0 is this height here. When will that happen? When will you get the same function, the same value for the function? At what value of x will you get that? So I want to know what value of x can I put in here. I have delta t at some later time. Delta t is positive. I have v. What value of x will this function, f of x minus v delta t, what value of x will this equal f0? Remember, f0 comes from putting x equals 0 and t equals 0 into this function. So can you see what value of x will do that? Give you the exact same value, f0. What do you think? So if I put x equals 0 here, I have f of minus v delta t. F of minus v delta t is not the same as f of 0. Right? The argument is different. So the function will usually be different. But I want to know what the argument is so that I get exactly f0 for sure. So you're saying x equals v delta t. Is that what you're saying? So this will be 0. OK. Delta t is positive. V is speed, so it's positive. Is x positive or negative? Positive. So this form is for a wave moving to the right. What do you think the form is for a wave moving to the left? It's not f of x minus vt. It's going to be g of something else. What is that something else going to be? All right, so this is moving left, and this here is moving right. So we've made some progress here. Any wave moving to the right can be written this way. Can be just written with f of x minus vt. You can have a pulse moving to the right. You can have an oscillation moving to the right. You can have a Gaussian. Anything that I write here, this manual thing, anything I do, whoop, whoop, that can be written as some function like that. That could be, that could be anything moving to the right. All right? To get it to move to the left, I'd have to move that little, what is this, pliers. I'd have to move it to the other side. All right? Okay. So that's pretty amazing. Any function of this form describes a wave. Any function whatsoever. And what the function is determined purely by how I move this. It's determined by the source. This would be called the source of the wave. S-O-U-R-C-E. Source of the wave. We're going to do this exercise. So here's what you have. Here's a wave at t equals 0. It's moving to the right. The velocity is 1 meter per second. Each of these things is a meter. So it's moving to the right. It has a velocity. So this shape is going to move to the right. All right? So what you need to do is draw a line like this and put -5, -4, -3 up to 5. And then I want you to draw where this peak is at t equals 2, then at t equals 4. So why don't you do that first? It's pretty easy. What does that look like at t equals 2 and at t equals 4? So the pulse just moves to the right. Doesn't change shape. Just moves to the right. When you're done with that, you can do the last point. It's a little trickier. I want you to sketch a plot of this, not as a function of position, but as a function of time at x equals 1 meter. So you want to look right here, and you want to know what happens at this point here as a function of time. Clearly, at t equals 0, it's at 0. All right? What about t equals 1 second? Where is it? What about t equals 2 seconds? What is it? T equals 3, etc. Okay? If you're done with the first part, sketch this as a function of time. So you're looking at this position here, and you want to know what this looks like as a function of time. All right? So we're going to have a graph. That's t. All right? And we're going to have 0. Let's say 1, 2, 3, 4, 5, 6, whatever. It's 1, 2, 3, 7. T is in seconds. And I'll give you a hint that t equals 0, which is right here. It's 0 at 1. So you know it's going to look like this. That's 1 point. Let's look at, I'm not going to draw it, but we can look at the other one. At t equals 2 seconds, this point will just be over here, right? And then it's just going to be the same graph. Just move this whole thing over by 2 seconds. And at t equals 4, this point will be over here. Okay, everybody got that? Any questions on that part? So now let's do the other thing, the function of time. At t equals 0, this point's over here. Okay, so the disturbance at here is what? 0. What about at t equals 1? It's still 0 because this point is over there. So t equals 1, it's still 0. Maybe I'll use purple. At t equals 2 seconds, we're looking at this, then this point will be over here. Right? So that's about halfway up. So at t equals 2, it's over there. At t equals 3, then this point will be over here, right? 1, 2, 3. That's up there. So that is up there. Did I do that right? Yeah. Then at t equals 4, this point will be there, and at t equals 5, that point. So we'll have 2 points up there, like that. And then at t equals 6, so 1, 2, 3, 4, 5, 6, it's that point. It's down to 0. So it's going to look like this. And if we draw it, go like this, and then afterwards, it's 0. So that's what it is. Notice an interesting thing. It's inverted from the, this has a shallower slope, and this is steeper. This part is inverted from the other, right? So the time graph goes the opposite way as the space graph. So our goal now is to describe this. I'm going to write down a function that has this form here. So we'll call this sinusoidal waves. All right, so I have y of x and t is some amplitude times the sine, and I'm going to put in kx minus vt. K is some constant. So that's a function of x minus vt. It describes this here. Okay? I'm going to multiply through by k, and I get sine kx minus kv. And I'm going to define this kv, I'm going to define it equal to omega. And we'll see in a minute what that means, why I do that. So then I get this equals a sine kx minus omega t. All right. Now the first thing I wanted to talk about is the units and dimensions. All right. Now units are different from dimension. Dimension is things like kilograms, seconds, meters. Units are the kind of dimension in some cases, but there's some units that don't have dimension. They have no dimension whatsoever. Anyone know of any unit that has no dimensions? What was that? Radians, very good. Radians have no dimensions. They are what we call dimensionless. Degrees is another one that's like that. No dimensions. The argument of the sine or cosine or a logarithm, any function like that in physics never has dimensions. It may have units like radians, but not dimensions. Because it physically would not make sense for the argument to have dimensions. All right? So that means kx is dimensionless. X has units of meters, so k must have units of 1 over meters. T has units of time, omega must have units of 1 over time. All right. Let's see if we can figure out what this k and this omega mean. What do they mean physically in the system? All right? So I'm going to start by working on this part. Here we have our wave. It's some wave. Right now, it looks pretty good. I can even set t equals 0. If I set, let's say this is time t equals 0. Then I get the sine of kx. And this is, in fact, looks like a sine wave. Because at x equals 0, if we called 0 there, the wave is 0. OK? So this wave is described by this function at t equals 0. So the wave goes like this. And here to here, right, this distance along the wave brings us from the corresponding point here to the exactly same point here. Or if you want, you go from here to here. So this distance here is what we call the wave length, right? So when we have a wave, this distance is the wavelength. So the question is, in going from, let's say, this point to this point, or this point to that point, how much did kx change? So let's do this point here. Kx equals 0 here, right, because x equals 0. What does kx equal here? I have to get exactly the same function, right? Same value for the argument. So what does kx equal to here? The sine of 0 also equals the sine of what? 2 pi. What about pi? Where's pi on this graph? That's pi. See, this point is not equivalent to this because at this point we're going up and at this point we're going down. But here we're also going up. So now we know something. We know kx equals 2 pi when x equals a wavelength, right? Because this is one wavelength from here to here. All right, so I can put in for x that, and I get k lambda equals 2 pi, and I get the result k equals 2 pi over lambda. And this is called the wave number. What it's telling you is how many waves there are per unit distance. So it's the number of waves per distance. So it has units of 1 over length, 1 over meters. If you continue in physics, you're going to see this wave number a lot. So make sure you understand it now. OK. All right, now we want to do the same thing for time. Same thing for time. So for example, if we look at this point, it's moving up and down, up and down, up and down. So it's doing it as a function of time. Let me see if we can actually see that. I'm going to put a timer in here. All right. So I'm going to run this. And I'm going to see when this point gets back up there again. It didn't run. How come it didn't run? Now it runs. OK, let's start over. It's too hard to follow. All right. The point is, this thing will go up and down, up and down. Now, just like kx changes with 2 pi, omega t will change with 2 pi for a specific value of x. And we call that the period of oscillation. All right, so let's see what that is. So if I do y versus time, I'll also get a sine wave like that. So this is at some value of x. OK? So like I can look at this value right here, and I could watch this green dot going up and down, up and down. It'll be a sine wave. And that sine wave will look like this. All right? So the time to go from one peak to the next, that has a name. What is that called? What do you think that's called? So what is this time from here to here? What is that called? What is that? Period. So that's the period. We symbolize it by capital T, and that equals the period. Just like up there, we have omega times the period is equal to 2 pi. So we have omega equals 2 pi over the period. And that's also equal to 2 pi times f. F is the frequency. It's in hertz, which equals cycles per second. And omega is the angular frequency, which is in radians. So now we have that. So here's our function. This describes that wave perfectly. A is the amplitude. So in this case, the distance from here to here would be A, or from here to here is A. Omega describes how fast it moves with time, and lambda wavelength describes the spacing in space. Now the question is, how do you determine these? How do you set it up? How do you give it a certain frequency, a certain wavelength? Notice down here, I can change the amplitude. I can change the frequency. I don't control directly the wavelength. We have that the amplitude of the wave and the frequency, omega or f, is determined by the source. So the source, A, and omega or f, determined by the source. So for example, if this is the source, I can only do two things. I can make it go bigger, and I can make it go faster. If I make it go faster, I'll make it go as fast as possible. Oops. Start. There it is. All right, so it's a much higher frequency. What happened to the wavelength? Did the wavelength go up or down? Went down. How do we know that? How do we understand that? Well, let's take a look at this equation right here. K is 2 pi over lambda times V. V is this, hope is the same. And omega is what? 2 pi f, right? That's what we have over there, 2 pi f. So we get that f lambda equals v. The fact that the wavelength went down suggests that v is a constant. The speed of the wave is a constant for the situation you're given. Can I change the speed? Well, I can by changing the rope or the tension on the rope. So if I make this tension higher, I can change it. So the frequency stayed the same. The wavelength got bigger, right? If I make the tension higher, the wavelength gets bigger. If I make the tension lower, the wavelength gets smaller. That's really too small. All right? That looks nicer. All right? I'll say in a minute a little more about that. The velocity or the speed of the wave is determined by the medium in which the wave exists. Speed determined by medium. All right, so there are various properties of the medium. So the speed of sound depends on air. However, if I'm underwater and I start screaming at you underwater, the speed is different. All right? It's less. In certain cases, it could be more or less. It depends on the medium. So the speed determined by the medium the wavelength, lambda, is just equal to v over f. So the wavelength, you cannot control directly. I can't make the wavelength, I can't change it by changing the source. I can't do it. I can change it by changing the medium, but that's because I'm changing the velocity. And then the wavelength is gotten from the velocity over the frequency. So we have this. The amplitude and the frequency are determined by the source. Amplitude determined by the source. Speed of the wave determined by the medium. And then the wavelength is just given by that formula. That's it. So how you set up the wave, how you oscillate, how you do it, that determines everything. It determines the amplitude and the frequency. And then the medium determines the velocity, the speed of the wave. Okay? I'm not going to derive these formulas. Some of them are derived in the textbook. But it turns out that the speed, the wave speed, is always given by the square root of some elastic property divided by some density. V is always equal to square root of an elastic property divided by some kind of density. All right? And we'll consider two examples. So the two examples are a rope or string. The speed is determined by the square root of T over, so T equals tension, U equals mass per length. So for example, let's say anyone here play a string instrument, like a violin, cello, bass, any of those? Nobody? All right. Guitar? Anyone play a guitar? Not very musical. All right. So if you look at a guitar, or a violin, or a viola, or a cello, or a bass, there's many strings. The strings have different thicknesses. That is so that they can do different mass per length, mass densities. The tension is controlled by the pegs on the instrument, so you can control the tension. That way you can control the velocity, all right? And then we'll learn later about standing waves. That leads to picking out various frequencies and wavelengths. So that's where it's very important. For sound in a fluid, V equals the square root of B over rho. So B is, we briefly touched on this, the bulk modulus. It's how the pressure changes with, how the volume changes with pressure. So you squeeze on the fluid, how much does the volume change? So that's an elastic property called the bulk modulus. And rho is just the mass density, mass per unit volume. So our textbook, I think, derives at least one, maybe both of those, if you want to see how it's derived. So that's how the velocity, the speed of the wave, all right? And we could see it illustrated in what we have here. So I make the tension lower. That makes the speed lower. The frequency was the same. So the wavelength has to get smaller, and that's what happens. So what you want to work on is understanding how this equation works in space and time. Now, one other crucial fact about waves is the wave disturbance moves, right? But no mass moves in the x direction. The mass just moves up or down. Or it might move a little bit in the x direction if you have what are called longitudinal waves. All right, so we have two kinds of waves. this is what's called a transverse wave, because the y is transverse perpendicular to x. So a transverse wave. All right? We can also have longitudinal waves. The best example of that for you to see is a slinky. Everybody know what a slinky is? It kind of looks a little like this. You know, it's like curled up, like curls. Okay? And the slinky can go like this and this. All right? So a slinky, if you set a vibration down a slinky, what happens is the coils get denser and less dense, denser, less dense, all the way down. That's called a longitudinal wave. All right? So let me write down those two things. So if y is perpendicular to x, that's called transverse. And if y is parallel to x, that's called longitudinal. So waves on a rope, transverse. Water waves that you see on the beach, transverse. Slinky, longitudinal. Sound, longitudinal. Sound waves in fluids are longitudinal. All right? As the sound from my mouth goes to your ear, the density is changing along the direction of propagation. All right? So as I'm speaking now, the density over here might go up a little bit, then down, up, down, along this direction. It's not going this way. It's going this way. The same as the direction of propagation. The only time sound can have transverse waves is in a solid, like in here. So sound can move in a crystal. There are both longitudinal and transverse waves inside a crystal. All right? We won't talk about how you calculate that, but you can know that. All right? So you have longitudinal and transverse waves. Light waves are transverse. Light waves are kind of interesting because there is no medium for light waves. All right? This is something that physicists in the early 1900s had to come to grips with because they couldn't even imagine a wave without something waving. What's waving for light waves is electric and magnetic fields, and you'll learn about that next semester, right? Do that next semester, you'll learn about light waves and what's called electromagnetic waves. So in a wave, the disturbance propagates, like in this example, in the x direction, but no mass moves from one place to another. So when you're hearing me, the air molecules in my mouth are not going to your ear. Instead, it's the oscillation in density and pressure that your ear is responding to. But energy goes from my mouth to your ear. So even though no mass moves, energy moves from my mouth to your ear. In this case, energy is moving from here and is propagating along the rope. All right? So waves are about energy propagation. Last thing I want to talk about is a little bit about, and I'm not going to derive any results, how do we know what the energy is in a wave? How much energy is there in a wave? So it turns out there are many ways of thinking about energy. you can think about the power that a wave has, which is telling you how much energy per unit time the wave has. Let's say I look at some spot on the wave and I look at how much power there is at that spot. So I can talk about the power of a wave. More common is to talk about the intensity of the wave, which is the energy per unit area per unit time. So you have the energy per unit area per unit time. So my voice, you get a higher intensity than somebody in the back. Why is that? Isn't the wave going all the way back there? So why isn't the intensity back there the same as here? Like, look at this guy. All right? Isn't the intensity over here the same as over here? The amplitude? Damping. Actually, it's relatively little damping. It could be, but my guess is that's not the main effect. I don't think there's interference, not much. Where is the sound going from my mouth? Where is it going? Is it only going to you? Is she the only one getting the sound? No. Where is it going? Can people in the front of the class hear me? Can you hear me? Say yes or no. Yes. Yeah. So even when I project it this way, they can hear it. What's going on? Well, this is a one-dimensional wave. The sound wave is three-dimensional. It's going in all directions. All right, so let's see what that looks like. Let's say my mouth is over here. Maybe I'm drawing my mouth a little bit. Let's see. There's my lips, and all right, there's me. And the wave is going out in all directions, all right? So at this distance, the energy all over here came from here. So the energy at this distance came from here. And then that same energy has to be spread out over there. So the energy per unit area is less here than here, because there's more area here. How much area is there here? This is a sphere. What's the area of a sphere? If you're at a distance r from the center of the sphere, what's the area of the sphere, the surface area? 4 pi r squared, all right? So it's 4 pi r squared. So that means the intensity goes as 1 over r squared, because if I multiply the intensity times the area, I have to get the same number. Energy is conserved. I mean, there might be a little bit lost to damping, but that's a small effect. All right? So the reason why I'm wearing a mic, actually that was kind of a fake when I went up there, because I don't know where the sound's coming from. It's coming from over there. All right? But there's also sound coming from my mouth. Okay? So the reason why I'm wearing the mic is because all of you in the back would get less intensity than here. And so the mic amplifies my sound, uses the speaker to make it louder. All right? But this is why the intensity goes as 1 over r squared. All of these quantities, intensity, power, or if I looked at the energy density of a wave, like let's say I took a piece of space and asked how much energy is there in that space due to the waves, they all are proportional to a squared, the amplitude squared. And the quantity, the proportionality constant can depend on all kinds of things. It depends on frequency, it depends on the kind of wave, etc. But the important point is the intensity power, all forms of energy go as the square of the amplitude of the wave. Okay? So if you average over some period of time, the average energy, the average intensity, the average power would be proportional to the square of the amplitude. So energy of a wave is proportional to A squared. Okay, the amplitude.